All right, guys. Just want to do a quick summary of what we have done so far, and stress on some conditions that must be met, just in order, just to run those tests. So we ran a z-test, we ran a t-test, and we did one prop c-test. In order to run the z-test, guys, you have to know population standard deviation sigma is given. They call it sigma, or this. It must be known. Known, that means he has to give you the value of this one. And if population is normally distributed, it doesn't matter what the sample size is. Sample size, any sample size. But if the population is not normally distributed, guys, what is the required sample size that we have to have? I touched on it today.
More than 30?
Yeah, exactly. N must be bigger than 30. Otherwise, you won't be able to perform the test. But if he asks you, just like I did in the problems, guys, perform the test, then you perform the test. But there are conditions. When we ask you in the book to perform the test, we're assuming that the conditions are met. Okay, for t-test, guys, sigma not known. So S is provided instead. Usually the t-test is used with the small sample sizes as well. So that's a condition here. The proportion z-test. There is a condition to run this test, but as you notice in all the question I ask you, I said just perform the test. So you just perform. But if he asks you, are the conditions of the test met or not, let me show you what the conditions of the test are. Very easy to verify. Okay. Let's say, let me just give you an example and show you how to verify the conditions. Let's say you want to test this. Okay, and let's say he gives you a sample size n equals 400. Okay, and it is beyond the scope of the course to discuss why the conditions are listed like that, but there are two conditions that we would have to verify in order to run the test. The first condition, guys, is condition number 1 is you have to verify that NP is greater than 5, and condition number 2, you have to verify that NQ is greater than 5. N is the 400 and P is the value that you pick up from the null hypothesis. So you just do, for number 1, 400 times 0.2, which gives you 80, which is bigger than 5. So we're good to do that. And then the second condition, guys, actually it's greater than or equal to 5. It is equal to 5, then that's good. And the second one is NQ. 400. Can someone tell me what do you think Q is? If P we're using 0.2, what would be Q? Q is a probability of failure. 0.8, which is 320 bigger. Well, it is bigger than 5. Then the conditions of the test are met. You can go ahead and run the test. If he asks you in a question in the homework online to check the conditions and you don't get more than 5 in both cases, you stop. You said the test cannot be performed. But these are critical, just conditions in order to run the proportion z test. NP greater than or equal to 5, and then N times Q is greater than or equal to 5. So this is for the proportion Z test. For the Z test, you know, when testing the mean, as I said, you must know sigma. T-test, sigma is not known, you just use T-test. For your information, guys, the Z-test and the T-test will produce pretty much the same results when the sample size is large. When you go beyond 30, you notice that whether it is a Z-test or T-test, you'll pretty much get the same results. But the T-test, you know, just is using with small sample sizes. As you notice in all the questions, the sample size was small. Small means below 30. Okay. Now, one more thing I would like to talk about, although on the test, guys, you're not going to see any questions pertaining to critical value, but when you do your homework online, and probably you notice when you seek help me solve this or show me an example, the author might try, you know, just to show you how to work out a hypothesis testing problem using an approach different from the p-value approach. The approach that I'm using, guys, in all the questions is called the p-value approach, but there is another approach called the critical value approach. I'm just gonna touch on it, you know, just for a few minutes and show you how the critical value approach, you know, just works. Let me just give you an example, guys. Let's suppose you have this hypothesis, and that's the claim. And let's suppose you have n equals 22. Let's suppose you have x bar equals 14.23. Let's suppose you have s equals 1.45 and alpha equals 0.05. If you're using the p-value approach, guys, you just use the t-test. You find the p-value, and if the p-value is less than alpha, you reject the null hypothesis. If the p-value is more than alpha, you fail to reject the null hypothesis. But let me show you the critical value approach. It would lead to the same results, but using slightly a different approach. So this is step number 1. Step number 2, guys, is the test statistic T, and I gave you a formula for that. And if you are to find T, guys, it will be X bar, which is 14.23 minus 15 divided by S, which is 1.45 divided by square root of 22. Okay. So we're not using, you know, the t-test here. I'm just going to show you the critical value approach. It might interest, you know, just some students, but I do, if you do the p-value approach, you should be fine on this test because you won't be asked to do one way or another. So you have the choice to do the p-value. Minus 15 divided by, how do you do this one, guys? You have to use a parentheses. You put 1.45 divided by square root of 22. And then close. Okay, I got negative 2.49, 491. Okay, how does the critical value approach work? You learned about the critical values when we did confidence intervals. So let me show you here. You draw this. You draw this curve. This is the T line. We're doing a t-test here. It's T because S is giving. And the critical value is the value that separates the rejection region from the non-rejection region, just like in the confidence interval. A critical value is a value that separates the confidence region from the non-confidence region. Because this is a left tail test, guys, the critical value is going to be on the left. It's some value right here. And this critical value, guys, in order to find it, you need alpha. So alpha is 5%. This critical value has an area to its left, which is alpha. if you remember when we did confidence intervals, guys, like a 90% confidence interval, then the critical regions will have 10%, 5% on one side and 5% on the other side. Here, because it is only one-sided test, it's just a left tail test. So whatever alpha is, that will be the area of the rejection region right here. So we need to find this value here. And I haven't probably mentioned, just how you find this one as far as T. We did it for Z. For Z, we just use inverse norm. But for your information, guys, if you go to your calculator right here, second and distribute, as you can see, after inverse norm, there is inverse T. So if you are using a T distribution, you can find the critical value using inverse T. It will require two things from you: the area to the left of the target, just like inverse norm, and requires the degrees of freedom. So if I press inverse T here, area, guys, is 0.05. And what is the degrees of freedom? N is 22. What would be the degrees of freedom here, guys? 21.
21.
Yeah. Watch. Okay, I got negative 1.72. So this value, negative 1.72, splits up the rejection region from the non-rejection region. Now, in order to make a decision whether you reject the null hypothesis or fail to reject the null hypothesis, you take the value in step number 2, negative 2.491, and place it on the number line right here, guys. If you place negative 2.491 in here, I think, guys, you should agree with me, it should be right here, because it's below negative 1.72. This is the rejection region. So what would be your decision, guys, since that the negative 2.491 fell inside the rejection region? What would be your decision about rejecting HO or failing to reject HO? Which one would it be? If this number falls on the line that belongs to the rejection region, you reject HO. If this number falls on the line outside of the rejection region, you fail to reject HO. For example, if this, guys, was negative 1.49, negative 1.49 on the number line would have been here, so then you fail to reject HO. So here, your decision will be to reject HO. And then you write the same conclusion. There is enough evidence at the 5% significance level to support the claim. This is what we call the critical value approach. This is called the critical value approach. Instead of finding p-value, we use alpha to find what we call a critical value. And then we compare step number 2 with this number. But with the p-value approach, guys, we compare step number 3, which is the p-value, we compare it with alpha. So it's pretty much like comparing apples with apples and then oranges with oranges. If I am to do this, guys, with the p-value, I'm going to get the same results. I'm going to reject HO. Watch. So stat, tests, t-test. Watch, I'm just going to do the input and see. I should get pretty much the same result. To mu0, guys, I have to put 15. I just made up this example to show you how that works. 14.23. S is 1.45. N is 22. And we're doing what? Less than? That is less than. Okay, let's find the p-value. Look at the p-value, guys. You see, you got negative 2.49. I got negative 2.49 right here, 1. And p-value is 0.0106, which you agree, guys, it is less than alpha, you reject HO. This is an optional method, guys. I just thought to give you just an overview of it. If you don't feel comfortable even doing any exercises with that one, that's fine. You don't have to, because I structured most of the problems, all of the problems, probably in chapter 7, so that you end up using the p-value approach. But just to show you that there is what we call a critical value approach in here. All right. What I would like to do now, guys, let me see how much time we have. Okay. I'm just going to spend a few minutes on the optional section. So then you'll be able to do the extra credit problem, just when it shows up, which is called testing the standard deviation. So let me just show you this. Okay, section 7.5. And then we'll go back and review. I'm going to answer some project question, and then we'll go back and review some more questions. Okay. You can see section 7.5 is testing for variances and standard deviation. So let me just do an example here and show you. So when you test a claim about the standard deviation, he will be asking you to test a claim about the standard deviation. For example, he'll be asking you to test a claim that sigma is less than 5, and this is how you would state the claim. You don't put mean, you don't put proportion, guys, anymore. You just have to use, so that's section 7.5. Let's say he says test the claim that the standard deviation is less than 5. So how do you state the null and the alternative hypothesis, guys? You state this. Sigma, you put sigma. You don't put P, you don't put the mean. You just put less than 5 and greater than or equal to 5. And this is where the claim is. Now, there are 4 more steps that you have to do in order to perform the test. So that's step number 1. Step number 2, I have to find the test statistic. Step number 3, you find the p-value. Step number 4, you make a decision to reject HO or fail to reject HO. And step number 5, guys, you write your conclusion in the context of the claim. When we are testing the standard deviation, we do not use a Z distribution or T distribution. We call a distribution. We use a distribution called chi-square distribution. And I'm going to show you this distribution here. This is how the distribution looks like. It's called chi-squared. What's one thing that is very different from the Z and T, guys, and the way I sketched, just the lines? There's something that you should notice right away that is totally different between Z and T when you compare Z and T with the chi-square distribution. Just look at it right here. Z or T can be negative. Chi-square distribution cannot be negative. Look, guys, we have to start with 0. The chi-square distribution, guys, looks like a distribution that is always skewed toward the right. It looks like this. And it is a family of curves. It has degrees of freedom, which is n-1. The larger the sample size, the more this distribution will be like a normal curve. The smaller the sample size, the more would be skewed, just toward the right. So this is a right skewed, just distribution. It's called chi-square. The total area under the curve is equal to 1. It can never be negative. It has to be a 0 and up. And this is the kind of distribution that we're going to be using to test the standard deviation. What I'm going to do right now, guys, I'm just going to solve an exercise showing you, just how to do this. And then on the test, there will be a similar exercise, just do it, where probably you have an opportunity, just to earn some extra points on this one. So let me just get to an exercise, just right away and show you how to work out the details. And the one on the test will be very much, just the same as as the one that we're gonna do right now. All right. Here is an example. I'm just gonna follow an example here to save time. It's already done the work here. A dairy processing company claims that the variance of the amount of fat in the whole milk processed by the company is no more than 0.25. Who can tell me what no more than 0.25 means?
Equal or less?
Exactly. And it says the variance, so it's sigma square. Variance means sigma square, standard deviation means sigma. So no more, less than or equal to 0.25. And you guys, you agree with me that I can put, just this one now greater than 0.25. And this is where the claim. You suspect this is wrong and find the random sample of n equals 41 containers has a variance of 0.27. Variance, guys, has a symbol which is s squared. Standard deviation has a symbol of s, and variance has a symbol of s squared, which is 0.27. At alpha equals 0.05, is there enough evidence to reject the company's claim? He's not asking you if you can support the claim, because when the claim in HO, he would not ask you a question of support. He'll ask you always a question of rejection. And he says, assume that the population is normally distributed. This is step number one, guys. Step number two will be to find the test statistic. And there is no program on the calculator can find it for you guys. You'll have to do it by hand. And it's a very easy formula for the test statistic. It's this. N minus 1 times S squared divided by sigma squared. That's a chi-square. That's the test statistic, which is N, guys, is 41 minus 1 times S squared is given 0.27. And can someone tell me what do I use for sigma squared? We assume the null hypothesis is true until proven otherwise. So what do you suggest we use for sigma squared?
0.25.
You got it. And if you do the math, I got the answer already there. 43.2. Step number 3, this is a right tail test. You just do this. You do that. I'm going to show you how to do this using the critical value approach. It is a right tail test. You shade an area to the right like this. And you put here the critical value, which is, we call it chi-square sub 0. That's the critical value. This value, guys, splits up the rejection region from the non-rejection region, and that's a 0. How we're going to find this one? We're going to use a table called table 6. And this table requires two things. We need alpha, and we need the degrees of freedom. Alpha here, he says it's 0.05. And degrees of freedom, we have 41 minus 1 will be 40. And let me just get the table. I will email it to you today. You should have it anyway. When you do any exercise that has to do with 7.5, this is going to pop up anyway. Okay. Look, guys, very easy to use table. It's already programmed this table to be a right tail test. So it's a right tail test. And this question is a right tail test. So just use the table as is. Alpha, 0.05. That's what I want. Degrees of freedom, guys, I need 40. Watch. I have a 40 here. Yes, I have a 40 right here. So it will be 55.758. Let me just change the color. That is the critical value. Okay, now how do you make a decision to reject HO or fail to reject HO? This one is called non-rejection region. Bring this step, number 2, and put it on the number line. Where do you think 42.2, guys, will be? Would it be before 55 or after 55? on the number line.
Before.
Before. I agree. Since it is before, you're going to fail to reject HO because that's a non-rejection region. And then 5, you say there is not enough. Just like before, nothing changes, guys. Evidence at the 5% level of significance to reject the claim. Because the claim happened to be in. So we say we don't have enough evidence to reject the claim. All right, guys. So this is an example. What I already have handout ready. I'm gonna send you, just a few more examples along with this, and then there will be one question on the test pertaining to this. I'll try, just to put a note, just on the question that this is for extra credit. But if you do it, great. You might get, just extra points. If you don't do it, it will not impact your score.
Can we use the calculator for step 3 or?
I'm gonna send you the handout for this one. I just need to do something else, but you can. There is a handout that I will be emailing you that it has also a calculator option, but it's not a particular test. It's something different, but you can use the calculator to find the p-value. So,
Okay.
and then if the p-value, remember, if the p-value is less than alpha, you reject HO. The p-value more than alpha, you fail to reject HO. But this table will pop up. If you need to use the critical value approach, this table is always available. And it is a right tail table, and you just use it. If you have a right tail test, you just use it as is. You pick up alpha, you pick up the degrees of freedom, and then you can find the critical value. Okay. Let me just stop this.